Okay, and so it's a pleasure, everyone, to have we have Dan Margalit from Georgia Tech, who's going to be telling us about Nilsen-Tёrston and Thurston a la Bears.
Good. Thanks, Andy. Thanks for having me. Sorry I am not there in person today. I will make it up sometime in the near future. Um, okay, so this is joint work with Jim Belk and Becca Winarski. I'm going to tell you the summary at the beginning. And yeah, before I even start, my goal is to make this as accessible as possible. So um, whatever questions you have, please ask, and I'll try to clear things up. So there's two theorems. There's something called the Nilsen-Tёrston classification, which is about surface homeomorphisms, and it's a way of giving a canonical form for those. This is one of the main theorems in the theory of mapping class groups. And there's another theorem that's just called Thurston's theorem, which is a similar canonical form, but instead of homeomorphisms, it's for branched covers of surfaces. So this is a major theorem in one-dimensional complex dynamics, because one way you get a branch cover of surfaces is to take, say, a polynomial. Okay, that's a branch cover of the complex plane over itself, or the Riemann sphere over itself. Okay, and the theme of today, or the goal, is to show that this is really one theorem, and we'll state them. I'll tell you what the theorems are, state them really as one theorem, and then describe a proof that proves them both at the same time and puts them into one context. Okay, so that's the goal. All right, so it's going to be a lot of expository explaining what these theorems are and how they fit together. All right, that's the summary. Okay, so we'll start with Nilsen-Tёrston, the Nilsen-Tёrston classification. What is it? And I have a slide for that. Oh, first I have a slide for what a surface is. So for this talk, a surface is just going to be a closed surface, a closed orientable surface, and it has some mark points on it. Okay, and I won't have any boundary or anything like that. All right, so those are what surfaces are for today. And usually the number of mark points will be finite. Okay, here's the first theorem. Okay, it's due to Thurston. The details were actually published in a book called Travaux de Thurston sur les surfaces, which came a little bit later. But the theorem is due to Thurston, and it builds on work that Nilsen had done earlier in the century. Okay, so the theorem is, if you have a homeomorphism of a surface, then up to homotopy, meaning there's a homeomorphism homotopic to it, that's one of these three types. And the first type is periodic. So some power of the homeomorphism is the identity. So an example of that is just taking the surface like this and rotating it by one click. That has order 3. The second type is reducible. So a homeomorphism is reducible if there's a one submanifold that is preserved as fixed or preserved by F. So just a collection of disjoint curves, essential curves. Okay.
Pointwise fixed or just mapped into itself?
It's mapped into itself. You could be permuting the curves, for example. Yeah. Once you're fixing a curve, you can kind of rotate it so that the curve is fixed pointwise, but you might be permuting them. Thanks for the question. And the last kind is called pseudo-Nosov. Okay. And pseudo-Nosov, the definition of pseudo-Nosov, it's a very special and specific type of homeomorphism. And the definition, which I didn't write out completely, is that there's two measured foliations, and F fixes both foliations, but multiplies one by lambda and the other one by 1 over lambda. Okay, so here is a surface of genus 2, and there's two foliations on it. And because it's genus 2, it's required to have the foliations have singularities. This is a 3-pronged singularity here for both foliations. And the picture you should have in mind is that so a square like this, because the foliations are being preserved, it should go to another rectangle, but it'll get stretched in one direction and contracted in the other. So this, if that's, I don't know, if that's set as U, F U would look like that. So that's the picture for a pseudo-Nosov. Okay, so that's my quick definition.
What are the requirements on the singular points?
Yeah, so that's going to be important later. I have a picture. It might be on the next slide. Oh, it's later. The singular points look like they have to look like this, or there's another special case. If there's a marked point here, I can have a one-pronged singularity. So they have to be modeled on these very exact pictures. So nothing else more wild than that can happen. Okay. The prototypical example of a pseudo-Anosov is an Anosov map of the torus. So here's a matrix, 2, 1, 1, 1. It acts on the plane, and when I teach freshman linear algebra, we just tell them about the two eigenspaces. Okay. But really, you can imagine that you have all these parallel lines parallel to all the eigenspaces, and that gives you two foliations of the plane that are preserved and stretched and contracted. And because this is an SL2Z, it descends down to the torus, and it gives you a map of the torus that preserves two transverse foliations, stretching and contracting. So you should just think, if this is familiar from linear algebra, more or less, so you should think of that happening on the surface of genus 2, except they're away from these finitely many singular points. Okay. Any other questions on how this classification works? Yeah, and you get a lot of mileage out of this theorem in the theory of mapping class groups. But one thing I'll say is that another way to state the theorem is that every mapping class is reducible. Maybe it doesn't reduce at all, but if it reduces, it could be trivially reducible. If it reduces into the other two kinds of pieces. So every mapping class has a possibly empty multicurve, and on the complementary pieces, the homeomorphism is either a finite order or it's pseudo-Anosov. So it's giving a normal form for every homeomorphism. Okay, if there's no other questions on that, that's one of the main theorems for today. So next I'm going to tell you about Thurston's theorem. Okay, and it'll sound similar. The setup is, instead of homeomorphisms, we're looking at branch covers. So just like before we were looking at homeomorphisms from our surface to itself, now we're looking at branch covers from a surface to itself. So I parenthesize itself branch covers. Okay, so S again is a surface with some number of mark points. F is a branch cover, which just means it's a covering space away from finitely many points. So after you delete a couple of points, it's a covering space. Okay, so P has to contain the post-critical set. So when you have a branch cover, there can be critical points. Like, for example, Z squared is critical at 0. It's 2 to 1 except at 0. Okay, so your mark points have to contain the post-critical set, and F of the mark set has to go into itself. And at least for today, the number of mark points is finite, but that's not essential really. Okay, so here's a map, Z to the D, that takes the Riemann sphere to itself. There's two critical points, 0 and infinity, and they both map to themselves with degree D. So this is called the portrait. You just write down all the critical points and the post-critical points, so forward images of critical points, and just write down what degree they map with. So any questions on that one? Or the definition? Just let me know. The next example is this matrix 3, 2, 2, 2 acting on the torus. That's the determinant of the matrix is 2. So this gives a twofold cover of the torus over itself. And I didn't have to mark any points because there's no critical points. I could mark some points also if I wanted to, because this is just a containment. Okay.
What are the points that you have to remove for Z squared?
Oh, for Z squared. Exactly. So away from 0 and infinity, it's actually a covering space. So every other point, it's 2 to 1. Right? You solve Z squared equals W, and you get two solutions. So it's
cool.
Yep, it's a nice covering space everywhere else.
Oh, cool.
And that's going to be the same in this next example here. So here we have the polynomial Z squared minus 1. So what's critical there? Infinity is critical. It's mapping with degree 2. That's this part here. 0 is mapping with degree 2 to -1. And -1, you plug that back into the polynomial, it goes back to 0. But that's not a critical point anymore, right? The critical points are where the derivative is 0, the derivative is 2z. So there's just that one critical point, well, that and infinity. So this is the portrait for that one. And again, if you delete those points, well, you also have to delete the other preimage of, so let's see, you have to delete one more preimage to make it an actual covering space. Okay. Good, any questions? Okay, so Thurston's theorem is going to be a normal form for these things. And here's the theorem. And it should look similar to the other theorem, a little bit at least. Although there's a definition here I haven't given you yet. So the theorem of Thurston, which came a little bit later from the other one, is up to homotopy, any of these self-branch covers is either a rational map or it has a Thurston obstruction, okay, which is like a reducing system. So this is like a reducing system in the mapping class group case. We're going to see that. This rational is the same as holomorphic. Okay, a holomorphic map from the sphere to itself is the same thing as a rational map. So you should think of those as the same thing. Okay, and again, Thurston didn't write down the details. Doherty and Hubbard did that later. Okay. Good. Any questions on that one?
What does it mean? Does it homotopy mean in this sense? Is the branching set is the geometry of the branching, the projection is preserved somehow?
Exactly. Yes, the homotopy has to fix. So when you have a branch cover,
Yeah.
two of these are the same. So you can have like another copy of this over on the left, and if they differ by maps that fix the set P, and are homotopic to the identity on the top and bottom.
Okay.
Yeah. Any other questions or comments? Okay.
So,
So,
do the homotopies move the marking on the bottom?
No, they can't move the marking on the top or the bottom.
Okay.
Yeah. Okay, so this is the foundational theorem in one-dimensional complex dynamics. All right, you have a map of the sphere over itself. You want to know, is it coming from a polynomial or a rational map? And this tells you, except I haven't told you what a Thurston obstruction is yet. So I'm going to tell you that next. Okay, so here's what a Thurston obstruction is. So when I have one of these branch covers, and I drew it suggestively as a sphere with a couple of necks, okay? A multicurve again is a collection of disjoint curves. It's stable if it's the preimage of the multicurve, which is another multicurve, contains the original multicurve up to isotopy or homotopy. Okay, so here we can see, in fact, I should add more to this picture. So maybe this. So here's a green curve. Its preimage contains this curve, and this curve here. Okay, and this other pinkish curve maybe just has one preimage. Okay, maybe it also has another one over here. So it's just a containment. Okay, that's what stable means. You should expect, because this is a higher degree map, you should expect the original multicurve to have many curves in its preimage that aren't the original multicurve. Okay, so that's what stable means. And again, you can have this phenomenon of having parallel components, even from different colors. So the colors mean like colors map to each other. And then you can just record this by a directed graph. Maybe this curve here is mapping to this one with degree 2, and this curve is mapping with degree 3, and this curve is mapping with degree 1. So it's some 2x2 matrix, right? You look at all the preimages, you look at all the preimages of the different curves and how many copies of them are mapping to each of the original curves. That's a 2x2 matrix. If there were two green curves here,
so shouldn't there be two? Since you have two red curves on the top, shouldn't there be two red things?
No, I'm only including the ones that are part of the original multicurve. So that this gets thrown away.
Ah, I see. Okay.
Yes. And if I had another green curve here, I would have to just add that to one of the entries of the matrix. So this green curve was the 3. So if there was another degree 2 curve right next to it, which could happen, then I would have to do 1/3 plus 1/2 here. So you record for each of the curves in the original multicurve, you look at all the preimages that are homotopic to the original multicurve. You take 1 over the degree, and you have to add together. If you see 2 of the same color that are next to each other, you have to add 1 over d for each one together. So it's so that's how you get the matrix. Okay. It's the exact detail. I mean, I'm happy to explain it, but hopefully you can believe that there's some matrix here going on. And this is called a Thurston obstruction if the operator norm is bigger than or equal to 1. And I'm going to explain why this is the obstruction to being rational, holomorphic or rational.
So is the operator norm, is that like the largest eigenvalue, or what's?
No. It's just like you look at all the points on the unit sphere, and it's like, yeah, the maximum amount of stretching you get.
Okay.
Right. So it's something like something like a largest eigenvalue, but it doesn't need to be an eigenvector.
I see. Okay, gotcha. Because it's real, so there might not be. Okay, might not be diagonalizable. Yeah.
Yeah, that's right. We don't. There's no reason this has to be diagonalizable. Right. Okay. So whatever this matrix is, even without hopefully have some idea that there's some way to get a matrix, I should be able to convince you that this is necessary if you want to have a holomorphic map. Okay. So that's on this slide. All right. So this is maybe one of the more technical slides, but it's, anyway. So a complex annulus. So the idea is you're going to suppose you have a complex structure and get a contradiction if the norm of the matrix is too big. So a complex annulus has a modulus. So every complex annulus is equivalent by holomorphism to an annulus that has inner circle, the unit circle, and outer circle, the circle of radius r. Okay, so
this is like the Riemann mapping theorem, but
yeah,
for anyone, right?
Yeah, there's a unique, yes, the Riemann mapping theorem will give you a unique r that makes this work. So so suppose you have a complex structure on your sphere, right? This is an annulus. It's going to be biholomorphic to exactly one of these, and log of that is the modulus of the annulus. Okay, so that's a measure you can put on an annulus. And then there's this fact from complex analysis that holomorphic maps should increase the moduli. Okay, and if it's holomorphic maps of degree greater than 1, strictly increase the modulus.
Mm-hmm.
Like if you do z squared, it takes this annulus to 1 r squared, and so you've doubled the modulus.
Yeah.
Okay, so that's a proof by example of this fact. Okay. Okay, but if the operator norm of that matrix was bigger than 1, that means you would have some multi-annulus, meaning a collection of disjoint annuli. And what is that matrix doing? It's recording how big these annuli are up here. Okay, so like when you take a degree D cover, we just saw z squared multiplies, well, going forward, z squared multiplies the modulus by 2. So if you go up through the holomorphic map, it divides by 2, the modulus. And so that's why you have 1 over something in that matrix. Okay, and you can also see that there's something predictable happens when you put 2 of these annuli together, right? The modulus adds. Okay, and so what that matrix is doing is checking if you can find some annuli, some annuli, a collection of annuli up here that when you map forward, the modulus doesn't increase. It doesn't decrease. It doesn't increase like it's supposed to. I guess the matrix is like going upward. I guess the matrix is telling us how the moduli change going up. And so since holomorphic maps are supposed to increase, and going up it's supposed to decrease, and that's why this is being bigger than 1 is the obstruction. So that's what the matrix is. It's just checking this. So this is like a natural obstruction, and yeah, Thurston's theorem is that's the only thing. If you don't have this problem, then you're rational, you're holomorphic. All right, good. Okay, so I just put Thurston's theorem up again. All right, so up to homotopy, any self-branch cover is either rational or has one of these Thurston obstructions. Okay. All right, so now I'll state the Uber theorem, which combines them both. There's not a lot of depth to this. It's just combining them into one theorem, but I'll explain. Actually, Lift theorem is maybe a little bit more appropriate, but you can name it whatever you want. So the theorem I'll just attribute it to Thurston in the 70s and 80s is up to isotopy, any branch cover is either holomorphic, reducible, or pseudo-Anosov. Okay. And holomorphic, when the degree is 1, holomorphic is the same as saying periodic. If you have a Riemann surface and you have a holomorphic homeomorphism, it has to be finite order. When the D is bigger than 1, holomorphic, as we said, is just rational. Okay, so these are the first two. This is the first 2 cases of the Nilsen-Tёrstona theorem and Thurston's theorem.
What was D again?
D is the degree of F.
Okay, got it.
Thanks for asking. And then there's a reducible case. In the mapping class group case, saying reducible just means there's some fixed multi-curve. But in the d bigger than 1 case, you have to do some more work to get the Thurston obstruction. Okay, so a Thurston obstruction isn't just an invariant multi-curve. It has to have this matrix, this operator norm being bigger than or equal to 1. So that's an extra argument you need. And then the third case is pseudo-Anosov, which by definition is d equals 1. Okay, so there's okay. So some notes on the side here. So Buff, Qui, and Tan generalized Thurston's theorem to the case. So for Thurston, P was the post-critical set, and they generalized it to the case where it contains the post-critical set, which is the setting we're in today. So we're getting that. Point number 2 is this settles the torus case. I think, as far as I know, it wasn't known whether you could have something pseudo-Anosov-like of degree bigger than 1 on the torus. And this is saying that can't happen. And even better, and I haven't seen this point of view before, that when you have a Thurston obstruction, you break up into pieces, and the pieces are holomorphic maps of higher degree and homeomorphisms. So your map can break up into holomorphic pieces and homeomorphisms, and those homeomorphisms you can apply the Nilsen-Tёrstona classification to. So that's why it's really one theorem. A higher degree map breaks up into holomorphic pieces and homeomorphisms that then fall into the Nilsen-Tёrstona classification. And so you can give one normal form. You have the holomorphic part, the rational part, and then on the homeomorphism pieces, you have these foliations that are being preserved if it's pseudo-Anosov, or you have some other complex structure that's being preserved if you're periodic. So it really is one theorem. Any questions? Okay, so this is nice, and sort of resolve some of these things. We also use our methods to answer a question of Bonk, which I'll talk about at the end. But what I like the most about this is that the proof, it's really one proof, and it's the proof that I knew, because I knew the proof of the Nilsen-Tёrstona classification from my work on mapping class groups, and that proof just extends to prove this theorem in higher degree. One thing to keep in mind is that for Euler characteristic reasons, if your map is higher degree, S has to be the sphere of the torus. Okay, so let's get towards the proof. The main ingredient in the proof is the work of Teichmüller from 1940 or so. Okay, yeah, Teichmüller space has a bad reputation. Teichmüller theory has a bad reputation of being hard to understand, but I'll try to give a high-level overview that hopefully will make sense. Okay, so the Teichmüller space, so we have our surface S with its mark points, is the set of complex structures on S, comma P. Okay, and modulo, you should think of this as modulo isotopy. So you can pull back a complex structure by a diffeomorphism that's isotopic to the identity. That's what the 0 means. And you just call that the same complex structure. You should think of this as complex structures up to isotopy. How do you put a complex structure on a surface? What you do is you just map it into the plane. So this, if you glue together those letters on that L shape, you get a surface of genus 2. And this is a chart of most of the inside of that L is a chart of most of the surface of genus 2 into the complex plane, which is the page here. Okay, and that extends in a unique way to a complex structure on the whole surface. So if I want to draw different complex structures on a genus 2 surface, I just modify the L shape. I can shear it, I can stretch it horizontally, and that's changing the complex structure. And then there's some mark points there. I can also move the mark points around. The torus is a little bit easier to understand. A complex structure boils down to just choosing parallelogram of unit area. Okay, those are the different complex structures on the torus. Okay, up to rotation. If I rotate the square, it's the same complex structure on the torus. Any questions on that?
So is in the case of higher genus, there's probably also some, if I draw a random polygon inside of complex space, there's probably 2 polygons probably give equivalent things sometimes.
That's right. That's right. So this is one way to represent that complex structure. I'm not claiming that all the complex structures on the genus two surface are L shapes.
And is it more elaborate than just rotation, or is it simply
Yes.
like rotation dilation thing?
Yeah, no, it's more elaborate than that. I can have two polygons that look different, and lo and behold, they're the same complex structure.
Okay, no, just checking.
Yeah, that's right.
Isn't there some theorem? I mean, like the once you have the polygon, you have a holomorphic one form, and if you've chosen the holomorphic one form, can't you then like just take DZ and then can't you like cut? Isn't there some theorem like you can then cut them apart and reassemble them if you have two things?
Yeah, so yeah, there's some way to maybe get a normal form for the polygon. I have to think about that before I say something definitive, but yeah, that might be right. There may be a normal form.
I mean, I think you have to have you have to take into account the one form. I mean, the form DZ, which descends to a one.
Yeah, so that's like a point in Teichmüller space with extra data.
Right.
Yeah, that's right. Okay, but that's how you should think of a Riemann surface. It's just you put a polygon, you have identifying sides together. That's a complex structure. Okay. All right. Now, Teichmüller defined a distance. I have two complex structures on the same surface. You want to say how different they are. How far apart are they? Okay, so X and Y are 2 points in Teichmüller space, so they're complex structures on S. Okay, well, you can look at maps F from X to Y, and I forgot to say here, homotopic to the identity. Okay, and you can look at that map and look at its dilatation. And yes, I mean dilatation, not dilation. It's a weird word. The dilatation of F, let's say F is smooth almost everywhere. You just look on the tangent space and little circles go to little ellipses, okay? And you look at the eccentricity of those ellipses. That's how dilated your map is at the point P. That's how it is at the point P, and the dilatation of the map is you take the worst point on the surface, okay? And then Teichmüller proved that there's a best map. There's a minimal map. There's a map H that has the lowest dilatation. Okay, and you take 1/2 the log of that. And don't worry about the 1/2, that's there for technical reasons. So here, pretend this is a torus, this square, and this rectangle is another torus, right? Those are two complex structures on the torus. What's the map from the square to the rectangle that has the least dilatation? Just the affine map, the obvious map where you just stretch and contract. Okay, that's actually a theorem. It's called Groch's problem. It's essentially Groch's problem.
And so I missed what the dilatation was at P. Was
at P
is the largest eigenvalue there, or?
Yeah, I guess is that the largest? It doesn't have to be an eigenvalue again. It's just like the operator norm, or it's like the ratio. Yeah.
Oh, okay. Yeah. It's not the ratio of the axis, right? It's sort of.
It's the ratio of the axes actually. So maybe that's different than the operator norm.
Okay. Yeah, that's different. Okay, gotcha. Thank you.
Yep. So so you can figure out what it should be for a square and a rectangle. It's just you take that affine map and right, it has the same derivative at every point. So now for this to go from here to here, this is the parallelogram with angle 45 degrees. It's much less obvious what the map is. It's not the shearing map. It's something else, and I'll actually explain on the next slide what it is. It's very mysterious. Like, how are you going to find the best map between those two? So already with the torus, it's already complicated. It's already subtle what the answer should be. Okay, any other questions on what this distance is?
What is H over here?
H is the best map. So you have the dilatation of F at a point, and you have the dilatation of F is like its worst point. And then Teichmüller proved that there is a best H. So the H is the best F.
H is the best dilatation. Is the dilatation of the best F, right?
No. Oh, you're right. I meant to put. Thank you. I'm going to add the word dilatation there. Yeah, that's a typo. Thank you. Yes, that was confusing. Okay, hopefully it makes more sense now. Any other questions? So yeah, you should be scared of this in the sense that, I mean, hopefully the definition makes sense, but how would you ever figure it out? Like, he proved that this H exists, how would you ever figure out what it is? Okay, and amazingly, he tells you exactly what it is. He tells you what H is, all right? And I'm going to show you that on the next slide. So this is my summary of Teichmüller's theorems. This is from 1940. he tells you exactly what the geodesics are in this space. Okay, so the geodesics are given by, you take two of these measured foliations, just like we saw earlier in the talk, not by coincidence, and you stretch along one and contract along the other. Those are the geodesics in the space. And moreover, there's a geodesic between any 2 points. Okay, so the geodesic between these, this is the first example. The geodesic is, you just stretch.
Geodesic, but a unique geodesic, right? Between
yes, I should say unique. I mean, there's Teichmüller's existence and uniqueness theorems. Yeah, I guess by, yeah, the unique. That's really important. Thank you, Andy. So the geodesic between these 2 points in the Teichmüller space of the torus is just you stretch, and that's like a path in Teichmüller space, and that's the geodesic. This here is the 45-degree parallelogram, but I rotated it because that's the same complex structure on the torus. Why did I rotate it? It's because if you take the eigenvalues for the 2, 1, 1, 1 map, which is appearing again, okay, take the foliations for the 2, 1, 1, 1 map, and take that matrix to the tth power. T is some real number, right? You're like slowly moving the x and y axes towards the eigenvectors, the big eigenvector, the eigenvalue, the bigger eigenvalue. Okay, and what it's going to do is it'll eventually take that square. If you choose t just right, some irrational number. If you choose t just right, you get this parallelogram, which after you rotate is the 45-degree parallelogram. So that's the best way to get from the square to the one that's sheared 45 degrees. That's the most efficient thing. And here, I just did the same thing on a genus 2 surface. That's a Teichmüller geodesic. You choose 2 foliations, do the same thing. And here, I was a little late. The singularities have to look like this. So here you have your transverse foliations. They can have degree 3, degree 4, degree 5. And if there's a marked point, you can also have degree 1. And that's going to be very important for the talk. So it's just totally amazing that you can list them all. And it's relatively easy to describe. But it's also hard to understand. I mean, this is kind of mind-boggling.
What is meant by singularity? Sorry.
So, right, when you have foliations, let's go back to, right, when you have these foliations on the surface, by Euler characteristic reasons, they have to have singularity somewhere, right? If the surface has non-zero Euler characteristic.
Oh, these are on the surface. When you do the gluing, these are the singularities of the foliation.
Exactly. So this L-shaped genus 2 surface has a singularity here, which you can't see, but it's because this is glued to some other sectors, and they adds up to more than 2 pi. Right? This is glued here, which is then glued here, which is then glued here, which is then glued here. I may have messed up, but anyway, there's a lot of sectors. Got it. So you have more than 2 pi, and that's.
I think every corner is glued plus the middle of each of the two long sides, right?
That might be right. Yeah, I see. Plus this. That might be right. I'm not sure. So these maps are called Teichmüller maps. Okay. All right. So that's the takeaway here. Is we know what the geodesics are. Yeah. So I hid the singularities in all these pictures. So I'm glad you asked. Okay. All right, so I'm at a point where I can state what we did. It's sort of.
I want to make another point that maybe maybe I was confused when I first learned this. In these Teichmüller geodesics, the singularities stay fixed, right?
Yes, that is correct.
Yeah. So like the stretching and contracting is all going along with the leaves, but the singularities stay where they are.
That's correct. Okay. Okay, so now I'll be able to state what we did and how it helps prove the Uber theorem. Okay, so Thurston defined a pullback map. So I've got a branched cover. There's a map from Teichmüller space to Teichmüller space. What's the map? Well, here's my cover. Here's F. What's a complex structure? You have open sets in S, and you have maps to the complex plane. If you have a branched cover, well, then you just compose and you get maps from upstairs to the complex plane, and that's the complex structure upstairs. So that's a map from Teichmüller space here to Teichmüller space here, but the top and bottom are the same, are both SP, and so it's a map from Teichmüller space to Teichmüller space. So this works whether the degree is 1 or bigger than 1. Okay. So any questions on the pullback map? That's going to be a star in the rest of the talk. All right, so given the branch cover F, sigma F is the pullback map. All right, so, okay, this I'm going to ask you to put in your pocket. I'll remind you of it. But so we talked about portraits, right? You have the critical point. So when you have one of these branch covers of a surface over itself, you have critical points. And actually, I wanted these to be not marked. So there's these two critical points, and they're mapping to these two post-critical points with degree 2. And then those map to these points, which then map to themselves. So if an arrow is unmarked, it's degree 1. So I showed you some portraits earlier in the talk. This is one that's either good or bad, depending on your point of view. It's a very, very special one. Okay. So the open circles here mean these are not marked. We only mark the post-critical points. Okay. So the point is there's just one very special portrait. Okay. So here's our proposition. The pullback map is a weak contraction, which means it makes distances not get bigger. The distance between sigma fx and sigma fy is less than or equal to the distance from x to y. And the square is a contraction, meaning points actually get closer, unless it's that one portrait. Okay. In the case of that one portrait, distances don't go down. Okay. And the proof is, this is almost the full proof, that Teichmüller geodesic, so you have a Teichmüller geodesic, right? That's happening, so you have this cover of, you really have a square. So you have S mapping over S, that's F, and you do a Teichmüller geodesic down here. That lifts to a Teichmüller geodesic up there. Okay, so if you stretch the complex structure downstairs, you can just stretch it upstairs. And so whatever distance you went before the pullback, you're going the same distance upstairs. Okay, so now you're supposed to ask me, well, wait, didn't you just prove this was an equal sign, right? Because you're doing these geodesics. Mark's already shaking his head. I think he sees the point. Unless this happens, okay? So you can have a marked point downstairs as you're doing your Teichmüller map, but then when you take the pre-image of the marked points upstairs, this marked point might be not marked. So you have something that looks like a Teichmüller map, but it's not, doesn't satisfy Teichmüller's definition, because you're not allowed to do this except at a singular point, at a marked point, I should say. And so in that case, by Teichmüller's theorems, like this map stretches the same amount as this map, but it's not a Teichmüller map, so there's an even better map, and that's why the distance went down. So this bottom of the slide is actually just our main contribution, but
that's a beautiful observation. I just
thank you. So we'll see. We get some consequences from this. So but this boils down to like the content of what we did. Okay. Any questions about that? Okay. So here's why that portrait is special. Okay. So on the sphere, these one-pronged singularities contribute +1/2 to the Euler characteristic. Okay, and all the higher prong singularities are negative Euler characteristic. So you have to have 4 of these to get up to Euler characteristic 2. Okay, and with this portrait, you can have your 4 one-prong singularities at these 4 points, and these were supposed to be a different color or unmarked or something. Okay, these are unmarked, but because that's degree 2 there, you get this one-prong singularity becomes a non-singularity, and so you don't have that problem on the previous slide where a one-pronged singularity lifts to junk. There's no that just doesn't happen in this example. So that's what's special about the portrait. This is the only way you can do it. This is the only way you can avoid having a one-pronged singularity downstairs lifting to junk upstairs, meaning this one-pronged singularity that's not at a marked point. Okay, so that's why that portrait is special. It's the only way you can do it. Okay, and for every other portrait, right? Since you have to have 4 of these one-pronged singularities to have Euler characteristic +2. for any other portrait, you want to show that some point of either f inverse of these 4 points or f minus 2, you want to show one of them is unmarked, and that's that junk point where you have the one-pronged singularity that's not a marked point. And it's just combinatorial topology. You're just counting. I shouldn't say just combinatorial topology, but it's just counting with the Riemann-Hurwitz formula, which I'll declare to be the fact that the sum of the local degrees of f minus 1 is always 2d minus 2. Okay, so right, there's a way to, d again is the degree of the map, and you can count the degree of the map by, so in this case, right, in this case we have, I add this minus 1 and this minus 1, that's 2. That tells me that the degree of the map is 2. Okay, and the other thing you need to know is that right, when you have a degree D map, every point should have D preimages, except if when you have a 2, right, that counts for two of the preimages. Okay, just like when you have Z squared, like 0 counts for 2 of the preimages. And so you just, now it's basically an exercise to show that this is true. Okay, and I'm going to prove it by example again. Okay, I'm going to try to make a counterexample by putting 4 marked points, and they're all mapping to themselves with degree 2. Okay, well, this avoids the problem, right? Because if I have a one-pronged singularity down here, yeah, it lifts to, whether or not these are marked, they unwrap to non-singular points. You don't get those garbage points. But what's the problem with this? If you add up 2 minus 1 plus 2 minus 1 plus 2, that adds up to 4. That tells me the degree has to be 3. So that means, whoops, there's another preimage of this marked point, and that's going to give me one of those junk points. That's how it works. So you're just playing off these two formulas. One of the things you can do here, which I don't think was known, if you have something like a topological polynomial, which is where there's a point called infinity that's mapping to itself with degree D. When you have a topological polynomial, sigma f is always contracting on the first iterate. You don't need the second iterate. It's just playing with these formulas again.
The topological polynomial is just something that is topologically conjugate to a polynomial, or?
No, not necessarily, right? It could be obstructed. It could have a Thurston obstruction.
Oh! It literally just means that the point, there's a point in infinity, and okay.
Yep. Yeah. So for those, sigma f is always contracting on the first go. But there is certain portraits where you need the second one, the second iterate. But it's just this combinatorial argument here, which is in, by the way, Hubbard has these great books where he proves Thurston's theorem and Nilsen-Tёrstona classification. And this is in, I think this is due to Duody and Hubbard, but I should credit them. This is not our argument.
The third volume just came out on the.
Yes, it's behind me right here. And I haven't taken it out of the package yet. That's
I've got it up on my shelf up there.
Too much mental energy to.
My camera's off. So.
Rip it open. Yeah. Okay, so that's that theorem, which is okay. Again, the theorem was that, or the proposition was that this map. So the way that Thurston's theorem was originally proven is an infinitesimal version of this. You show on the tangent space there's some on the tangent space there's a contraction. This is slightly stronger. But the point is, the proof is, just what I said. It's very, very simple. Okay, so now I'm going to prove the Uber theorem, which is who remembers what the statement is, but you're supposed to be given a branch cover, f, from a surface to itself, and you're supposed to say something about it. You're supposed to classify it into certain categories. Okay, and if you know the proof of the Nilsen-Tёrstona classification that's in, say, my book with Benson and Farb, you'll see this is the exact same proof. Okay. So given a branch cover, you define tau f. You should think of that as a translation distance. And it's the infimum of the distance of x and sigma fx. Okay, that's a number you can define. It's the infimum over all x in Teichmüller space. Okay, and there's just 3 cases, just like if you know the proof of the Nilsen-Tёrstona classification. Either it's 0 and realized, it's not realized, or it's positive and realized. Okay. If it's 0 and realized, that says the pullback map has a fixed point. That's saying you're holomorphic. There's some complex structure that's preserved. So that's just already done. If tau f is not realized, I think I'm not going to say anything about that today. I think it's too much. But I'll just say it's the same proof. If you know, if for those of you who know the mapping class group proof, it's Mumford compactness criterion. It's the same thing. Okay. If tau of f is not realized, you show that the complex structures are going off to infinity in Teichmüller space, and Mumford tells you that there's some curves that are getting shorter. Okay. So I want to explain case 3, which is tau f is greater than 0 and realized. So this is the holomorphic case. This is the reducible / obstructed case, and this is supposed to be the pseudo-Nosov case. Okay. All right, so how does that go? And I'm showing you this, and I know at least one person has seen the proof of the Nilsen-Tёrstona classification. This is the same picture. It's the exact same picture. Okay. So we're in the case where tau f is positive and realized. So you can choose an x that's minimal. That's what it means for the infimum to be realized. You take the geodesic gamma through x and sigma fx. That's this. And the claim is that the pullback map has to preserve gamma. Okay. And you might be worried at this point you don't remember Teichmüller's theorems, but this doesn't use anything. This is just a soft argument using the minimality of tau of x. Okay. So you take a point y in between x and sigma fx on the geodesic gamma. And what you're trying to rule out is that it goes over here, right? You want sigma fy to be here. You want it to be back on the geodesic again. That's what it means to preserve gamma. So you suppose it goes here, but by the triangle inequality, that means y moved less than x, so contradiction. In the proof of the Nilsen-Tёrstona classification, sigma f is an isometry. Here we have a weak contraction, but it's the same thing. It's the same argument. It doesn't matter. So, we're not done yet. So all we've proven is that if tau f is positive and realized, then there's a geodesic that's preserved. But remember, what's a geodesic in now you have to remember Teichmüller's theorems. What's a geodesic in Teichmüller space? It's your stretching and contracting along two transverse foliations. That's essentially the definition of a pseudo-Nosov homeomorphism. It's really that direct. Again, this is Bayer's contribution. He realized, wait, I've seen these foliations and stretching and contracting before. And so that's how he gave his proof of Thurston's theorem, which was not the original proof. Okay, so there's a couple of loose ends to tie up. So the above argument not only shows that sigma f preserves gamma, it shows that it's not an isometry on gamma. That takes a little more thought, but take my word for that, or figure it out, or ask me. So because it's an isometry of gamma, it preserves both foliations. Sigma f preserves both foliations, and therefore it preserves the Euclidean area. I didn't tell you this before, but when you have these two measured foliations, it's putting a Euclidean structure on the surface away from the singular points. And so the pullback map is preserving the Euclidean area. But if a covering map is preserving area, it better be degree 1, right? Otherwise it would multiply the degree. In general, it multiplies the degree by d, multiplies the area by d. So that's that loose end that ties up that the pseudo-Nosov has to be degree 1. There's no higher degree analog. Okay, that's it. That's essentially the proof of the Uber theorem. I also advertised, we answered some question of Mario Bonk. Here's the question and the answer. So suppose f is one of these branch covers, and we're assuming it has degree 1, and the surface is the sphere here. Is it true that f lifts to the torus, right? It's confusing because f is already a covering, but sometimes you can lift a covering to a covering of the torus over itself. Okay, and is it true that it lifts if and only if the portrait is special? Okay.
How could you lift from a sphere to the torus?
It's by the hyperelliptic involution. So
okay. You're right. You're right.
The diagram. Yeah.
Okay, gotcha.
Yeah. You're lifting a covering, which is weird, but you're lifting the covering of spheres to a covering of tori. So a degree 2 map of the sphere would give you a degree 2 map of tori by lifting by the hyperelliptic involution. Okay, the hyperelliptic involution is just this here, right? This rotating by pi. And our proposition is that yes, it's true. And the proof is the pullback map is never contracting, meaning I can find directions that lift to non-singular ones. So there's these 4 points, there's these 4 special points in the sphere that come from the fixed points of the hyperelliptic involution. I put all of my one-pronged singularities at those 4 points. Under the hyperelliptic involution, those unfold to become non-singular points, right? Degree 2, which is non-singular. So whenever you lift from the sphere to the torus, the pullback map is never contracting. Okay, the pullback map for a lifted map. So if you take an F downstairs and lift it up to the torus, the pullback map is never contracting because you have these directions where all of the singularities are here, which lift to regular points here. Okay, but if sigma F is contracting, then sigma F tilde is contracting. So these are just in opposition to each other unless you have this special portrait where you don't have contraction. Okay. So that's how you get the if and only if. And why is sigma F contracting if and only if sigma F tilde is contracting? Just because a point in Teichmüller space down here gives you point in Teichmüller space up here by pulling back through the hyperelliptic involution. So there's a direct correspondence between the Teichmüller spaces and the pullback maps.
Sorry, Dan, I have a question. It's not clear to me if one of these directions is clear and the other one isn't, or are both not clear, like a priori.
Yeah, the part that was not known is the only if. If the portrait is special, then
I see. You can just sort of construct these foliations manually somehow.
Yeah, if the portrait is special, you always get an embedding of Teichmüller spaces. What's the point? I think I'm actually proving both directions at once here. I don't know why the other one was known already. I agree, it's not obvious. It's a good point that it's not obvious that that you lift if the portrait is special. I guess I have to think about that. But one thing I want to say here is that this is really a topological fact. I mean, we're using Teichmüller space here, but I'd like to find a proof that doesn't use Teichmüller space. I think I'll need to think for a second to give you a better answer to your question, Nick. In the last few seconds, I just want to show you just an idea of what some of the open problems are. I'm not going to go on about these, but just there's lots of open questions here for people who know about mapping class groups or homeomorphisms of surfaces. This one's easy to state. When is the pullback map constant? It's not known. If and only if. Here's a proposed answer. Is it constant if and only if the pullback on curves is like you take any essential curve and keep pulling back, does it always eventually become trivial? Pilgrim's global attractor problem is also about lifting curves on these surfaces through the self-branch cover and just asking, is there always a finite set of curves that get pulled towards? There's recognition problems. Somebody hands you a branch cover of a sphere. Which polynomial are you looking at? Which rational map are you looking at? This is just kind of a sampling of some of the things that people think about in this area. And so, yeah, hopefully I've given you some idea of what we did and why that's an exciting field. Thank you very much.
Okay, sorry, I had to click a bunch of things to make everyone visible on the screen now and for the video. So does anyone have any questions? So I'll lead off. So is there any hope to deal with things that aren't a branch cover of a surface to itself, but to have some sort of classification of branch covers from one surface to another surface?
Oh, very interesting. See, the problem is you need the dynamics, right? You need to be able to apply the map over and over again. And if you have two different surfaces, you just can't do it. So I don't know that there's I would love it if there was a good way to formulate that. One of the problems here is just like list for me all the conjugacy classes of degree D maps with, you know, n post-critical points.
Right.
Okay. And so again, you could ask for a way of, but I think that's known. I think Bernstein and Edmonds, you know, give you a way of classifying all the branch covers. So I have a feeling that's like the version I'm stating is known. Maybe there's another version that's interesting, but I don't know.
I mean, there are restrictions, like, you know, you still have some pullback back between Teichmüller spaces, and there's restrictions on maps between holomorphic maps between Teichmüller space, right? So there should be about that.
I see. I think I see what you're saying. Yeah, all these proofs are dynamical, but maybe it's a really good idea, but I don't know.
So, any other questions? Well, let's thank Dan again.
Yes,
Go ahead.
I'm just curious, what was the relation between like the kind of singularity and like or the characteristics?
Yeah, so the one-prong singularities count for +1/2, and in general, you take the number of prongs, subtract 2, divide by 2, and maybe there's a minus sign in front, and that's the and then there's a minus sign in front. That's the contribution of each singularity. So,
and you said that, and you said somehow like the connection with like that and like the Euler characteristic comes from Uran-Hurwitz.
Or
something else.
Yeah, what is it called?
Poincare-Hopf.
Yeah, thank you.
I mean, it's all just all a variation on that theme.
It's a variation on that theme.
You have to pass to a double cover so things are orientable, and then it really is the Euler characteristic. It really is the count of the zeros of a vector field.
Yeah, that's right. So it's most closely related to vector fields. Singularities, you pretend these are the flow lines of a vector field.
Cool.
Yeah.
So if there's no further questions, let's thank Dan again. For real this time.
Thanks for having me.